Hello and welcome to this little tutorial about how to do the same effect that we can see on games like Octopath Traveler, where we have a 2D sprite in a 3D world that reacts to the transition and rotation of the camera. We can see in this little demo what we are going to achieve today. And if I move, I have not implemented the movement animations, but it's a good starting point for everything that comes after making this system work. This system is usually called billboarding because we're using a texture that will be facing to the camera. So let's get into it. First, we will do this using blueprints. So, in order to have everything clear before programming, it's nice to have a little whiteboard. And why not use a little literal whiteboard? And here we will create the flow that we will use to program this functionality. So first, we need to update the rotation of the sprite. So let's call it update rotation of sprite. How do we update this? What values do we need? We need to get the camera. And in order to get the direction of the camera, we need its location and its rotation. So I'll put here get camera transform, and I'll move it right over here. And the thing that we would do is this, and please forgive my doodles. Let's say that this is the 3D space. Oh, I can show it here. It's a lot better. This is a 3D space, right? So my camera is right here. Let's say it's in this point and it's projecting this image. So we have something like this. And here we have the direction of the characters. And this is really important because it will be in base of this direction. For example, this character will be looking this way and this other character is looking that way. With this value, we will get the information in order to know which sprite to use. So let's break it down a little bit more. What do we need first in order for this to work is for the texture to always look at the camera. So how our diagram will look? First, we need the camera information. Then we will need to make the texture look, and let's call it sprite look always, and it will be between quotes because it's not always, but always most of the time. Toward camera. Let me move it here. And why is it always in quotes? Because if I'm looking upwards with my camera, I do not necessarily want for the the character to look this way, because it will seem as it will be floating, and we don't really want that. If we want to polish this example a little bit more, we could make the values of the it would be pitch. We can clamp that values so we don't get to this extreme and we see the top part and we realize, oh, it's just a plane. So yeah, whenever we make this sprite look towards the camera, then we need to know which direction the character is facing. And with that information, then we can determine if the character should be looking forward, back, to the side. So determine which direction the character is looking at. And finally, with this information, we can select the correct sprite to show. And I'm gonna move this, I'm gonna delete this one because it's the same as this, and we need a place to start this diagram, and we need to update it every X seconds, or we could update it every tick. Update. And now we should have a clear view of whatever of the thing we're trying to make. That's nice. So let me encapsulate everything into nice boxes. I do not have a tablet to draw, so please keep that in mind. That didn't. There it is. And yeah, every tick it will update and will run this logic, get camera transform, then it will make the texture or a sprite look always towards the camera. We determine which direction we're looking at, and then select the correct sprite. And that would be the end. Whoops. There it is. And another shape. Yeah, that's a lot better than my arrows, but you guys get the point. This is the diagram that we will be following. And because I know that doing it from zero takes longer, and most of you guys probably just want to know how to do it. So let's overview how this demo was created. I used as a base the third-person character because it already contains code that I will use anyway. For example, let me check if this is being possessed. Yes. I'll make auto possess this character. That is the third-person character. And if I play, this character already has a camera that rotates with the mouse. It already moves with the W, A, S, and D. And you can see that it works even if I'm not using a character that is using a sprite. and well, it jumps and everything. So what I have done is duplicate this blueprint that contains only input code. It contains an skeletal mesh, an arrow mesh that will show the direction that the character is looking, and a character movement component that is the one that has all the logic for walking, jumping, running, swimming, etc. So in my Octopath character, this is exactly the same code. It is exactly the same structure, but I have added a paper sprite. And this component is the one that will be holding a source sprite. And it has a lot of values that we can tweak. But we won't be seeing any of those in this video. Also, we could get rid of this character mesh, of this skeletal mesh component, but this was a simple example of how to do this type of effect, and to get rid of it, we would not need to create a pawn, add the character movement component, and the setup would take longer. So an easy way to do it is just select none in the skeletal mesh, and even though you are creating a skeletal mesh component that it won't be used, it really doesn't impact the performance too much. So a paper sprite is the one that we need, and I have imported sprites from the game. Let me see if I can show you. Window, content browser 4. And for example, Ophelia, this is the sprite sheet. And in order to get every sprite and divide it, you can just right click, sprite actions, extract sprites. In this case, this sprite sheet is not distributed equally, so I can't use the grid mode, because this would mean that, for example, we have 1, 2, 3, 4, 6, 24. We could divide it by 24, but we see that it really doesn't align properly. So in this specific case, the auto mode was the way to go. And pressing extract will give us all these files. In my case, I'm just using these ones, that looking forward, looking to the side, and looking backwards. So with all these assets in place, let me close this one. What we're doing here is pretty simple. Every tick, I'm calling a custom event called update sprite rotation. This is the same as our diagram, but I'm encapsulating all this behavior in one custom event. So every tick I'm calling update sprite rotation. This is, if we double click, we will go to the custom event that is right here. And first, we are setting up the rotation of the sprite. We have the camera transform right here. Get player camera manager. And in this case, I only need the camera location. So we can check this. Now we need to make the texture sprite look always towards the camera. Well, we are finding the look at rotation of the actor to the camera. So that function will do exactly this part of this one. I'm just setting a vector that is the position of the actor that is looking, and a vector here that is the look at. So if we return to blueprints, find look at rotation, we have the start, that it will be the actor. The actor will be this one. This is the actor, and this would be the camera. So it will be a direction looking towards the camera. And I'm only returning the jaw because I don't want it to rotate with the roll of the camera or with the pitch. If I connected the pitch, we can see what happens here. Yeah, it gives us bad results. So yeah, we only need the jaw value. So let's disconnect it. And I'm combining this rotator because this character, this direction is looking towards the positive x-axis. But if I reset this to 0, we see that it's looking towards the y-axis. And this would be fine. This usually gets corrected here in the viewport, but it's the same correction here. So because we are setting the word rotation, whatever change I did here, for example 0, it's still gonna work properly. So if I wanted to take that in account, now that I'm looking this for a second time, we could get no, not the mesh, the paper sprite, get the, let's see, yeah, C is minus 90. We could get the relative location, and it would be the same. I know one is, oh, but yeah, it's not the it's not the same because I'm combining the rotation, and this gets a new rotation, so it keeps adding it. So yeah, that's probably why I left this value as a hard-coded value. If you don't want to use a value like this, you could, in the construction script, get save the relative rotation, and let's not call it relative rotation, start relative rotation. Yeah, I should append the start at the start. Yeah, well, and with this, it won't change every time, and it will work almost the same. Well, not in this case, because the values are rotated. This is giving me, now that I double check, minus 90, and this was receiving only 90. So let's leave it at that. So now it's working correctly. And here we just set up the new rotation. That would mean that this part is done. Now we need to determine which direction the character is looking at, so we can select the correct sprite to show. And I have created a macro so it's easier, but the values going into the macro, it's getting the camera manager, the camera location again, the get actor location It's almost exactly the same, but what changes? We just need to get that direction vector from the actor towards the camera. And well, this little part of the code, what it's doing is setting up the C value to be the same as the actor location C value. So what does this mean? And I'm gonna create a camera here. Let's camera. In the case, and I'm gonna position it here. Let's say, yeah, I'm gonna pilot this so we can look toward this. If my camera is not at the same level, we're not gonna get the results we need. So what this part of the code is doing is translating the camera to the same level of the actor. So if I can draw it here, that will be a better representation of what is happening. What that code does, this is the vector. Let's say that is the position of this character. This is the position of the camera. And what this does is just, it let the camera keeps the x-axis and the y-axis, but the c-axis makes it equal to the one here. So the position I'm really using for the other calculation will be one nearly here. So this will be the vector that I'm using for the camera location. So yeah, with these two values, we can get the unique direction. This direction would be, in this case, this one. It's not, remember, it's not this one, it's not this direction, because what I'm doing is making the C value equal to the actor. So it's really this direction that I'm interested. And I'm doing this because now with this vector I can compare with the actor direction, and it will be in the same plane. And this operation will be easier to manage with a dot product. And having both of these vectors will be easier if they are in the same plane. So let me see if it now goes to the dot product. Yeah, here it is. We're zeroing out the C vector now that we have the direction that we need. So it's almost as doing a two-dimension operation. So here we get the actor forward vector, do a dot product, then the actor right vector, and do a dot product. Now, if you guys are not familiar with dot product, a simple explanation will be that it will compare the direction of the vectors and give you a result, a scalar result, based on that operation. For example, the common cases are, if I do a dot product of this vector and a dot product of this one, the value that will be returned will be 0 because they are not associated in any way. They are orthogonal to them. But if I was doing a dot vector of these two green vectors, then the value would be 1. So it's an easy way to know the relationship between vectors. And if I did a dot product operation with this green vector and this orange vector, it will give me -1. Any value in between will be inside the -1 and 1 range. This would probably -0.8, -0.8, and so on. So it's an easy way to see if the character is looking, if it's in front or is backward, and that's exactly what these two values will give me. This will give me a value between -1 and 1, and this will be in relationship with the forward vector of the character and the right vector of the character. And the macro just compares. We have a little variable that it would be, in this case, 0.8, because if we go to the example, let's look it from above. My camera is coming from this way, and my character is looking this way. Well, in this case, it's looking backwards. Let me press play. So yeah, there it is. That's a better example. No, yeah, there it is. So this character is looking this way. This character is looking this way, and my camera will be something like this. Now, if I do a dot product with this vector, it would probably return, it's not exactly the same, so it won't be 1, but it would probably be 0.9. If I did a dot product with these two vectors, it would return to me maybe minus 0.87. But if I change the camera, now the vectors are a little different. Let's say this was looking this way, and this is looking that way. Now here, the dot product between these two values would be 0.7, and between this other vector would be minus probably 0.8. And in order to tell the code that it's looking to the side, I'm using that value that in this case is 0.8. So if it's lower or higher, because we are dealing with 0.7, and if I go to the back, it will be minus 0.7. So if it goes beyond that threshold, I would use the side animation. And that's exactly what happened here. Let's say this is greater than 0.8, then it's looking forward. If it isn't, then we check if it's looking backwards. So we multiply this 0.8 by a negative number, -1, and we get minus 0.8. And if it's less, then it's looking backwards. And the right value will help us to determine if it's looking to the right or to the left. And we're doing the same operation, just using the right vector instead of the forward vector. And the macro will check if it's about a positive value, then it would take it as right. If it's a negative value, it would take it as left. I have put a little print strings for debug that right now it's disabled. But if we ignore this, we see that here we have a set sprite action. And forward sprite, back sprite, left sprite, right sprite. This way, whenever we are looking, yeah, now I see why it was working in an inverse position. This is face right, but I'm using the left sprite here. Yeah, let's fix it, because if I want to share the code with you guys, then it should be really clean. Yeah, left, and let's do what I was doing here. It's not really 90, it's minus 90, because it's a double-sided sprite, so I wouldn't be able to know if it's really looking forward or backward. Yeah, that's working properly now. I start relative location, so we don't need a magic number right there, right? We just need, oh, where does it look properly here? Maybe if I on purpose left it like this, it will give me a bad result, right? Yeah. So we can fix it like this, and the viewport change, because we're setting it here and saving it to a variable, will respond to it. So yeah, no more magic numbers in the code. As I mentioned, this is just getting rid of the C dimension, so it's easier to process these numbers. And that's it. That's basically it. That's a code. It's a code that it will run every tick. If you don't want to depend on a tick, you can change it to a timer. For example, like this, timer. Well, a start timer. No? Timer. It was set timer. Yeah, set timer by event. We can set it here, and in the begin play, we call it. And now this is not gonna execute every tick. Maybe it isn't necessary, but with the frequency that I want, maybe it's 0.1 seconds, and I'll put it on looping, and it will work almost the same. You could possibly see the delay if we make it update every 1 second. Yeah, you can see it now. But you can play with the values. This would mean that because we're using a timer instead of the tick, we could actually disable where it is, and this is like optimizations to the max. We can disable the tick here, and it will still be working, because the timer does not uses the blueprint. It uses its own classes to do the functionality of executing more than once. So we're optimizing to the max. We can play here, and now it's really smooth. Yeah, a lot more smooth. But we could also use the event tick Also, another optimization that I just realized is we could check if we are already in this, if we're already using the forward sprite, so we don't have to set it again, but we're just adding a check that would be almost the same. This operation is really not that costly. But yeah, that's it. That's all I wanted to show to you. And you can leave any questions or uh, any topics that you want to explore. We will be there to help you guys out. So hopefully this was useful to you, and see you in the next video.